A steel pipe in an industrial cooling system looks solid and static. Zoom in close enough, and that surface reveals a highly active chemical battleground. Water flows over the metal, stripping away material pit by pit. This degradation, what we call corrosion, is driven entirely by the exchange of electrons. It happens on a microscopic scale, invisible to the human eye, but with enough time, it destroys heavy infrastructure. Facility technicians cannot stop this decay if they only view the system qualitatively. Knowing that a pipe is rusting is useless without understanding the exact chemical exchanges causing it. Monitoring dials and flow rates provides a macro-level view of the facility. To keep those systems running, that operational data has to be paired with a rigorous understanding of chemical mechanics. We will build the mechanics of fluid control from the ground up. We will track how an atom's valence shell determines its reactivity, calculate exact chemical concentrations using molarity, and observe how systems adjust under pressure through dynamic equilibrium. Mastering these principles separates reactive maintenance, waiting for a pipe to burst, from proactive, engineered system control. The starting point for any chemical interaction is the structure of the atom itself. A dense nucleus of protons and neutrons sits at the center, surrounded by orbiting electrons. It is the outermost boundary of this structure, the valence shell, that dictates how an element behaves in a fluid system. All chemical reactions happen here. Atoms naturally seek the lowest possible energy state. That thermodynamic stability is achieved through an inert gas configuration, meaning the valence shell is completely full with 8 electrons. Once full, the atom stops reacting. Highly reactive elements possess an incomplete shell. The alkali metals in group 1A of the periodic table, for example, have only a single valence electron orbiting alone. To reach a stable state, these metals must shed that single electron. This structural instability causes alkali metals like sodium or potassium to react violently when they are introduced to water. On the opposite side of the spectrum are the halogens in group 7A. They are missing exactly 1 electron to complete their shell, making them aggressive scavengers that strip electrons from anything they touch. An element's structural position on the periodic table predicts its threat level or utility when introduced into a facility's fluid system. The interaction of these valence electrons creates the chemical bonds that hold facility infrastructure together. Metals achieve stability through a metallic bond. Instead of holding tightly to their outer electrons, metal atoms pull them across an entire crystal lattice, creating a fluid sea of shared negative charge. This free-flowing electron sea allows the individual metal atoms to slide past one another. It is why pipes can be bent during installation and why they conduct heat and electricity so effectively. Ionic bonds involve a complete physical transfer of 1 or more electrons from one atom to another, resulting in 2 oppositely charged ions. Because these opposite charges attract, the newly formed ions snap together into a rigid 3-dimensional grid, exactly like the structure of sodium chloride. Corrosion is the physical process of environmental reactants breaking metallic bonds and forcing them into ionic bonds. The metal lattice dissolves into the surrounding fluid. Treating industrial water involves chemically protecting the metallic bonds of the infrastructure from favorable ionic exchanges. Preventing that ionic breakdown requires precise chemical dosing across thousands of gallons of fluid. We treat these systems using solutions, a homogeneous mixture where a solvent, usually water, dissolves a specific treatment solute. Operators cannot measure that solute strictly by mass. A gram of sulfur contains twice as many atoms as a gram of oxygen. Dosing a system by pounds means you cannot track the actual number of reactive particles in the pipes. Chemists solve this using the mole. A mole is a fixed quantity. It guarantees exactly 6.022 times 10 to the 23rd atoms or molecules of any substance. 1 mole of a dense element has a higher gram molecular weight than 1 mole of a light element. They weigh different amounts, but they deliver the exact same number of reactive particles to the system. This gives us molarity, represented by a capital M. Molarity is the number of moles of solute divided by the liters of solution. It defines the exact chemical concentration of the fluid. For acid and base treatments, operators use normality, a specialized metric that tracks the exact equivalence of available hydrogen or hydroxyl ions in a liter of solution. Qualitative guesses lead to equipment failure. Molarity and normality provide the mathematical language required to control the fluid environment and keep the infrastructure intact. Even a perfectly dosed, saturated solution is never static. It exists in dynamic equilibrium, where the rate of solid particles dissolving is perfectly matched by dissolved particles precipitating back into solids. Those rates remain equal only as long as the conditions of the environment remain constant. Le Chatelier's principle dictates that if a stress is applied to a system at equilibrium, the system will actively shift to minimize that stress. If a dissolving process is endothermic, meaning it absorbs heat, then a temperature rise acts as a stress. To consume that excess heat, the equilibrium shifts to the right, dissolving more solid material and increasing the solubility. Conversely, if the process is exothermic and releases heat, raising the fluid temperature forces the dissolved particles to precipitate out of the solution to relieve the thermal stress. On the facility floor, this happens constantly. When a heavy pump engages or a heat exchanger activates, it exerts a pressure or thermal stress that instantly alters the chemical balance of the cooling water within it. Le Chatelier's principle allows operators to calculate exactly how mechanical and thermal changes will impact chemical stability. They anticipate the shift and adjust their dosing before the infrastructure takes damage. An industrial facility is a unified machine spanning multiple scales of physics. Thermal and mechanical stresses dictated by Le Chatelier dictate the exact molarity required to keep a system stable. Maintaining that precise molarity is the only defense against structural metals surrendering their electrons and dissolving into ionic bonds. And that entire chain of macroscale events is driven by the inescapable drive of microscopic valence electrons seeking a full outer shell. By mastering these first principles, facility operators engineer the fluid environment to force the exact physical outcomes the facility demands to survive.